Today we're going to talk about the new Unity render pipeline. Unity supports a great variety of games. These games, they vary between different art styles. So some games, they are very stylized, while some other games are photorealistic. And they also require different rendering needs. Some games, they don't require much complex lighting. They're mostly baked or not real-time lighting at all. And some other games require very complex lighting setup. On top of that, game developers, they want to maximize their platform reach. So they want to ship their game to multiple platforms. And it is reasonable to expect that the game developers will not spend a lot of time optimizing their game for every single platform. So we need to provide our developers a rendering solution that works fast everywhere. But this is not an easy feat to do. It's mostly because these platforms, they vary greatly in terms of features and architecture. So one optimization that works well on console, for instance, it might not scale down well for mobile. And even if you just consider the mobile ecosystem, it is very fragmented. So we still have to take different approaches regarding optimization. And so there's a conflict here that we want to be fast and deliver more features to our game developers. But because we support a lot of platforms, we have to make sure that every feature works everywhere, or at least there's a fallback to them on some platforms, and that with every new feature that we develop, we don't regress performance on any platform. So our solution to this is scriptable render pipelines, or for short, SRP. So SRP is, we exposed rendering code to userland. So users can describe rendering at a high level with C#. On top of this API, we provide 2 rendering pipelines out of the box, and one of them is the lightweight render pipeline. So the lightweight render pipeline focuses on mobile performance and platform reach, while the high definition pipeline focuses on state-of-the-art rendering and AAA content and performance on high-end platforms. These pipelines, they are open source. So with them, we also expose to the users how rendering happens with Unity. So it's not a black box anymore. The users can see what's going on. And they can even use these render pipelines as a reference to implement their own specialized solution. Today, we're going to talk about the lightweight render pipeline. And this pipeline is built on top of this API. It was developed from scratch with the mobile performance in mind. And it supports a broad range of platforms. So we still support the low-end devices with GLES2, but we go up to consoles as well. And the rendering scales between these. But we don't only want to improve the performance, but we also want to improve the workflow and the way you can extend the pipeline with your custom effects. This rendering pipeline is out of preview now, so it means it is ready for production, and we encourage you guys to try and use it in your games.
So there's some multiple ways to get lightweight render pipeline. One of them is through our new kind of entry into Unity. It's the Unity Hub. This is essentially our kind of front page now for dealing with anything Unity. Here, when you start a new project, you'll obviously get the new project name, where you want to save it, what Unity version you want to use. But there'll also be the templates drop down. You will probably recognize this. It was in the Unity launcher by default. But here you can choose lightweight render pipeline. And this actually loads up a project that will look like this once it's open. This is a good little scene. It's just kind of like, it's got the basic setup. It's got some lightweight render pipeline assets already created, and they're already set up at kind of like some good low, medium, and high settings. And it's all assigned in the graphic settings, ready to go with a little scene to just play around with. Now, if you want to start from scratch, or you want to try and upgrade, maybe you've got a small project you've been playing around with and you want to try and use lightweight render pipeline with it, you can also get lightweight from within Unity. This is through the package manager, so you can find this through the window package manager. This will load up the package manager window. Packages are essentially the new way we go distributing kind of add-on features and some of our main kind of tools that we're starting to develop. Lightweight and the SRPs are found in this tool. So on the side, you can find a big list of all the packages that Unity has out currently. And here you'll find Lightweight Render Pipeline amongst the list. You can just select it and then go install. And also you can open up the drop down and see all the previous versions that existed. You'll also see some things like tag for verified. This means it's gone through proper full level testing through everything and is shipped with the editor at that point. Currently we're using 5.xx for 19.1 and 6.xx for 19.2.
So one of the things that we want to take a look at is performance, and we're going to talk about built-in pipeline and lightweight render pipeline. So the built-in pipeline is our previous rendering solution that was with Unity before 19.1. So we want to make a comparison in terms of performance here, but we also want to make a fair comparison. So in this scenario, we have the built-in and lightweight using the same rendering strategy, so they're doing a forward renderer. And we also guarantee with this project that they have the same quality settings, so you should get roughly the same images on your game. This performance project is available online for you to test, and this was one of the, so this is more like to users asked for this, so they can also check on the devices and compare performance. And with these scenes, we are interested in seeing these 4 common bottlenecks that you might find for your game. So view rate is basically the amount of fragments that you can shade and display on the screen. Draw core GPUs, the amount of work that you can submit, the amount of geometry that you can submit to the GPU. The draw core CPUs, the cost that you have to set the render state to render each object and draw cores. And bandwidth is the reads and writes that you do to external device memory. So not only the bandwidth impacts performance, but it impacts power consumption on your device, which will make it overheat. And if it overheats, it will throttle down, which impact also performance. Okay, so let's take a look at that. So first, there's a lot of things happening on this screen, and I'll take some time to explain them. So these bars, they represent the amount of times on average. We tested a few mobile devices and we averaged their results. So these bars, they represent the average of how much faster lightweight is compared to built-in in this specific scene. Since this is an average, some devices will perform better or worse than that. It's important to say that lightweight is currently not supported, not faster on every device that we tested. There are a couple regressions we found, but we're taking them as bugs and we're fixing them at the moment. So, okay, so this is the view rate test. This is basically comparing the physically based shading of lightweight compared to built-in. The first thing you might notice is that there's a slightly difference in image, and it is because lightweight is doing physically based light attenuation, so it's more physically correct, while the built-in pipeline is doing light attenuation based on the light range. So artists, they had to decrease the light range to achieve the fall off that they want. But the downside of that was that you might end up with big light ranges, and so light's touching a lot of objects, and that will be bad for performance. So in lightweight, you increase the light intensity, and that's it. Here's another test. This one is, it has a moderate amount of draw cores. We're doing shadows with 4 cascades. And we are doing a depth pre-pass in this one to guarantee that we submit a lot of work to the GPU. And here you can see how the lightweight compares between, it has some difference between devices and averages in different APIs. There's another one is CPU. So this thing has about almost 3K primitives being rendered. All of them use different materials. So it means there is a cost to set these materials. You're going to see there's a slightly image difference. It's because those materials are randomly generated. So it happened that in this screenshot, there are some few saturated materials on lightweight side. But yeah, so here's how they compare. And then this is bandwidth. So this scene is heavy in terms of bandwidth cost. So it has HDR, MSA, it's resolving shadows in screen space. It has soft particles. Yeah. And you can check this project in the GitHub link I linked before. Okay, so let's also take another look at how the forward render differs from the built-in pipeline. So this is a scene from Angry Bots 2 running in built-in and lightweight, and they're very close to image quality. So this is what you get in the device. And you're going to see that the built-in has more draw calls. And of course, here more draw calls is worse. And the reason is that lightweight, one thing that it does different is that it shades all of the lights in a single pass, so it rendered the objects once, while the built-in pipeline will render objects for each light and composite the light on top. So it's not only more draw calls, but it's also more overdraw. And there's another thing that a lot of users, they complain about, that a built-in pipeline always do a depth pre-pass, and they want the depth, but they don't want to pay the cost of a depth pre-pass. So in lightweight, in some cases, the depth pre-pass will still happen. For instance, if you're resolving shadows in screen space, we still have to do that. But in some other cases, we don't do the depth pre-pass, and instead use the depth from rendering of the opaques. So it's not only that the draw calls are less in general, but the cost of each draw call is also less. So when rendering objects, we have to set up some render state, and there is some data that we have to upload to GPU. And we group objects that has the same render state to minimize the render state changes. This is what we call batching. And the batching, it works differently between the built-in pipeline and lightweight render pipeline. So in the built-in pipeline, the batch happens per material, while if you have two objects with different materials, the built-in pipeline will build a constant buffer before rendering each one of them and upload to GPU. And this happens every frame, so the data is not persistent. Every new frame you're rendering these objects, it will build this data again. While the lightweight pipeline, it batches per shader. So if you have two objects with two separate materials, but the shader is the same, it means we'll build the data once for all of that batch, and then we'll submit this data to the GPU once again while we offset the specific positions of the constant buffer. And then the data is persistent on the GPU. So we build it once, the next frame is there, it's cached. We don't have to spend CPU time doing that again. And they will only change if the material changes, if you have animated material that changes the properties and so on. So the SRP batch is experimental in lightweight. You can enable or disable it in the pipeline asset settings, which is what controls the quality settings of lightweight. The shaders, they require some special setup to glue the constant buffer to the engine. So if you're using the shaders that we provide with lightweight or shaders that are created with shader graph, you don't have to do anything. They'll be compatible. And the batch is supported on a few platforms, and we are adding support to more platforms soon. If you're writing shaders yourself with HLSL, then you have to follow a few rules. One of them is that all of your material data has to be declared in a C buffer. It's called unity per material. This is the glue that requires the engine to make this data persistent. And then now when you click on the shader, you're going to have this SRP batcher compatible or not. If it is not compatible, it will still render fine, so you have no issues. But it just means that the data will be on the slow path. It will fall back to slow path that we build the data every frame for every object. So skin meshes don't support the batcher, and objects that you draw with material property blocks don't, because basically the batch is alternative to material property blocks, so you don't have to use them anymore.
So another thing we wanted to make a bit better with the new SRPs and Lightweight was improving the workflow as well, because performance is great, but if it's not easy to use, it's not that great. So biggest one probably is we've finally got a shader graph, which is lovely. It's really nice to be able to make materials and shaders with nodes. Something as an artist or a technical artist coming to this it's just super useful. It's, you know, you don't have to go in, you don't have to worry about knowing all the glue that holds these shaders together, because they can be quite complex and they do a lot in the background for you. Shader graph makes it nice and easy. So it's quick for iteration, because, well, you can just try things out. You don't have to write bunches and bunches of code. And in this respect, it's also really nice because in Shader Graph, you can generate the code, right? You can actually look at it, then go in and do any custom code, like shader code on top of it if you want to start editing it. The code is pretty readable and it's pretty nice that gets outputted. So if you want your artists to go nuts with this, you can give it to them. They can throw in all the nodes. Then you can just compile out the code and do any like little tweaks on top if you want to. But the shaders themselves that get produced are really nice and really clean. As you see, it's really easy to do something like this. It's just using some normals and some heights, and it's just blending it together. You no longer need to keep going back and forth between someone who's more familiar with HLSL. Another improvement we wanted to do was just some of the UI stuff, and we started with the shaders because the material UIs were quite complex, and we had a lot of shaders built in Unity, and a lot of them weren't in any way related. We had some called base map, some called main text, some called albedo, and it was just kind of a mismatch of like visual information. So in Lightweight, we wanted to clean this up a bit. We wanted to create some nice categories that were familiar across the different shaders, even though the shaders might do completely different things. If you've got, like, for instance, we've now added full culling options, so you can render the front face, back face, or both. This should be the same across all the shaders. Like, it doesn't make any sense for it to appear differently. So this is one thing we wanted to make sure was consistent. We've also added some things like the blending, so we've got full blending controls. And also, we changed how render queue worked. Before, you kind of chose whether it was going to be an opaque or transparent, or you could put in a completely custom number, say like 2,500, and that would be halfway into the opaque, or 3,000 something, and you're in transparent land. Here, we wanted to kind of make it more like simple and also be able to go back and forth between different passes, because something that's opaque should always render in opaque. You shouldn't be able to take an opaque shader and actually tell it to go into the opaque render queue, which you can get some weird, funky rendering. So the new way is more of an offset, and if you change between transparent and opaque, the offset stays the same. You could offset it -10 or +10, and it's going to work regardless of what the shader is actually doing in the background. Another thing we wanted to actually improve was before, if you want to do some certain special effects, it was quite common to use a color texture or a depth texture. And in built-in, the color texture was generally known as a grab pass in a shader. The depth texture, you set some flags on the actual camera to tell it what the depth mode was and render it out. Or rely on something like post-processing to kind of trigger it to create it. In Lightweight, we wanted to make it very obvious what you're, like, if you wanted it, you want to tick it on. So we've got it in our render pipeline asset under the general, the first option. We've got depth texture and opaque texture. It's called opaque texture because it does render straight after the opaque pass is finished, so it only contains objects that are in the opaque pass. But this means it only gets triggered once, and you can use it as many times as you want in the transparent queue or later, and it's not going to cost you. So grab pass before, every time you used it, it would actually recapture the scene at that point. So you could have it throughout a transparent queue or even throughout an opaque. It would just keep adding to that performance bottles. So we also have nodes for these, which is quite useful. So in Shader Graph, we have a scene color node and a scene depth node. Both of these just simply output the values at those points. And you can also supply custom UVs if you want to do some distortion effects or kind of rechange the sampling. Something else we wanted to make a bit more clear was when you obviously got some rendering issues, you want to figure out what's going on. Looking through the profiler or frame debugger, the built-in was a bit of a mess. There was a lot of stuff kind of hidden. The hierarchy was quite interesting. I don't know why we chose to do some of the things we did. But in Lightweight, we wanted to just make it nice and clear. Each pass that gets executed is in the order it's getting executed. If we're switching the render target, we have that in there. So we know at that point we're changing, we're doing read, we're doing stores, and we didn't want any guesswork. So we've also added the ability to group by cameras. So we can see here, this example, there's actually 4 different cameras for a split screen game. And you can go into each one and see the exact passes that they're triggering. This also obviously works when you run to a device like iOS or Android. You can connect to it and see it exactly the same there.
All right, so another thing that we've done is to improve the customization, and there was a lot of feedback that we received about this, so we recently improved this a lot. So in built-in Unity, if you wanted to extend the pipeline with some custom rendering features, then you could do it by implementing some rendering callbacks, or you could inject command buffers in specific events in the light or in the camera. So Lightweight pipeline, we wanted to do it easier and a more robust system for you. So the Lightweight render pipeline is data-oriented pipeline. So basically you configure data, and some things have data and logic. So the renderer, we have this concept of the renderer. The renderer is just a scriptable object that contains data to create resources. And then this renderer contains render passes, a logic to execute render passes. And we expose through the UI what we call render features. So if you look at this, here we have some render features there, and it's basically custom injected render features. So we have a feature to do a data path, character paths, and we're going to show this in a demo soon after this talk. Oh, in this talk, I'm sorry. And then the way these features are injecting render passes in specific parts of the pipeline. And the render passes, they can execute command buffers, or they can do a wide draw objects call with some filters. You can create resources and configure targets and so on. So it might be that you want to render your character with some outline when it goes behind a wall, and then you can inject a render pass to do that. These features, they're also scriptable objects. They contain data, and they contain logic to inject render passes at specific points. And Lightweight uses reflection to pick up all of the features that you have in your project, and those will be available on this drop-down list to be added to the renderer. So this is how you do, if you're asset store, or if you're a team that develops like middleware for other teams, then you can create these features, and then your technical artists will be able to come here and configure the features without any code at all in a very easy and friendly way. So for instance, in this case, we provide Lightweight render pipeline with the render objects feature. It is a very generic one, but these other two, they are features that exist in our project that were picked up by the system. So renderers in Lightweight, we make it available now, one forward renderer. That's a fallback renderer. It works everywhere. It does the single light loop shading that reduces the draw calls and overdraw like we talked before. In 19.2, we are delivering a 2D renderer, and this 2D renderer is going to support shape lights and pixel perfect and some other cool features. In 19.3, we are working on the third demo, the third renderer that is going to be mobile friendly in terms of bandwidth cost, so it should be good to use on mobile. But it might be that this is not enough for you, so it might be that you want a different rendering solution, and you should not create a pipeline from scratch by doing this. So it might be that you want to do some cluster tile-based lighting with compute shaders to compute the light lists, or it might be that you want a stylized rendering with some stylized shadows. Or it might be that your specific game, you know some restrictions, so you can tweak the current renders to do something that you need. And these renders, they're just scriptable objects that you can assign to and override the pipeline with them. So you can create them, and you can override them on a global basis. So in the pipeline asset, you can override the renderer to render all cameras for your project, including the scene view camera. Or you can override on a per camera basis. And on the camera now, there's a setting that you can select render type, then you go custom, and then you drag and drop your renderer to it. And the good thing about these renderers is that you should not worry too much about stereo rendering or editor rendering. It should be automatically handled by you. You just worry about injecting render passes and configuring the state and the targets of each render pass. And then things like the gizmos, the outline when you select something, scene view, they should just work. And basically, this is how you achieve that. You subclass this scriptable render class, and basically you want to implement a few methods and have some data. But then the setup method is where you implement your render passes. So you create your render passes and inject them. The setup lights is where you compute the light lists and you submit the light data to the GPU. And the setup culling parameters, you can control some input to the culling system. So it might be that you want to control the shadow distance to call some shadow casters beyond that distance, or it might be that you want to do per object light culling. So yeah.
Okay, so now we're going to go through some demos showing this new feature. And one example we're going to show is doing outlines for Toon. So this is quite a common thing. A lot of people like to do it. And since we made a scriptable render pipeline, by default, we don't do multi-pass rendering. So if you put in multiple passes in your shader, only the first one is executed. So we needed a solution. So we've got this little scene here. We've got some characters and we've got these towers. You may have seen these. They were getting used quite a bit throughout Unity. They're really cool little assets we got. So this is the perfect kind of art style where we would want some Toon outlines. So let's show how you can do that with these new render features. So if we select our lightweight render pipeline asset, you'll see now up the top here, we've got a renderer type under the general settings. By default, it's a forward renderer. We can override this. So we can override this with a custom forward renderer. We don't need to worry about doing any code for this necessarily, because we just want to essentially reuse the forward renderer, and we just want to add some new render features to it. So if we change it to custom, you'll see a drop down with the data, and here we've got a forward renderer data. This is the one that is shipped with lightweight render pipeline, so it's the default one, it's read-only, it's in the package folder. So we want to make a new one. So if we go down to the project view, we can right-click, we go create, rendering, lightweight render pipeline, and we can choose a forward renderer. Now what this does is it creates a custom forward renderer. We have a few settings, and we have our list of render features that we can start adding to. So I'll just name this outline first. And in this demo, you'll actually see another one here. There's a hull effect. That'll be a different type of outline we'll do. This one, we'll do a Sobel filter post effect. So this could be done with the post-processing stack. You could write a post-processing effect and shader and put it through that system. But here it's quite nice because we can actually inject it wherever we want in lightweight render pipeline. So to do this, we can go up here into our custom forward renderer, and we can add to our list. Now in this project, we do have all of these scripts actually in this project. And as Philippe has said before, we're making the render objects one part of lightweight. And first off, it'll be experimental while we iron out some of the UI and UX parts. But for this example, I will use a blit. So essentially this will be, it'll blit to the screen with a material and a shader. Let's call this outline. And we can open up the settings. We've got some options here. Now this one's just been made. We threw it together quickly for this project. Main thing I want to do here is put in a blit material. So we've got a Sobel shader we made earlier. So I'll just use that one. So we can call this Zobel filter. Oop, I could spell correctly. And we will find that shader. And I believe it is under Unlit Zobel filter. Now we go back to our outline post forward renderer, and we can drag this material in. Now, nothing's happened, and this is because I haven't actually assigned this forward renderer to be used. It's still using the custom one that's in the package. So if we go back to the render pipeline asset, we actually want to replace this here. So I will drag our outline post up into the data, and now you see all our characters have an outline on them. It's a very thin outline. I actually want it a bit thicker, so I can go back to this material. I'll just crank this up a little bit. Now, you'll see the characters have quite a thick outline, but the buildings, for some reason, have a thin outline. And if we go down here to the frame debug, we enable it, we can actually see all of our passes here. And what we can see is we've got the render outline, render opaques, doesn't have the outline. Come down, do the copy depth, and then we do our outline. Now the outline looks really thick here for the buildings, and it's consistent with everything. So what's happening here? Oh, well, we go down here, we see the skybox is actually eating into our outline. So this isn't ideal. We actually want to make sure we're doing our outline after the skybox. So let's go back to our project, select our outline post, and let's change the event that we're actually rendering. So you may have seen this if you started doing some customization to Lightweight. This is essentially our kind of callbacks for injecting render passes in certain points in the pipeline. So here we can just choose after rendering skybox. And then we'll see our outline is popped back to be a nice consistent shape around it all. And if we go back to the frame debug, we will see it's in the right place now. So let's try another effect. Let's try the hull effect that I was talking about. This one is another way of doing toon outlines where you actually choose your objects, you invert the normals, you push them out a bit, and you give it the color of the outline that you want. So for us to do this, let's make sure we're using our hull effect custom forward renderer, sorry, and we lose our effect. So let's start setting this one up. Now we say we like the background the way it is. We just want the outline to actually affect the characters. So this time we'll use the render objects because we want to render a certain set of objects with some settings that are tweaked. Let's call this outline hull effect. Now, we've got some options here. We've got the similar again, the event. This is choosing where it's getting injected. We've got a filters. This essentially is filtering what objects we're rendering. And we've got some overrides here. And these are to override certain parts of what we're rendering again. For this example, I actually just want to render these characters. And these characters have been set up with a character layer tag. So if we select this mage here, we can see the layer is set to character. So in our hull effect, we can actually change the layer mask here from nothing. And we want to just render our characters again. So right now, all this is actually doing is just re-rendering the characters over top of themselves. This isn't ideal. We need to actually replace the shader and the material that is rendering those characters. So let's go to overrides. Now, we have a material slot here, which means we can give it another material to override. So here I can go create. We'll call this hull. And we've actually got a toon outline shader that also has been created. If we go toon and go basic outline. And all this shader is essentially doing is rendering the geometry black, pushing the vertices out along their normal, and doing culling set to back faces only. I mean front faces, so the back faces are the only ones that are rendering. So if we go to the hull effect, assign this material override, we see you get a very tiny outline. And again, setting's not high enough. So let's go back to the hull effect, and let's just up this outline width. And we see we start to get a nice outline around these characters. Now, this we can also have a look and go into our frame debugger again. And we can see here after our render opaques, we have the outline hull effect. And we can see it goes through and renders each character and their items with this new shader. So this can be used to do all sorts of crazy effects, which is quite cool. One thing is that this is attached to the scriptable render pipeline asset. So this means everything is rendered with this now. If I briefly go into the scene view, we can see we get our toon outline effect here as well, which is really nice. This is consistent, and this is where later on we'll show the kind of power of being able to do it on a per camera basis or per pipeline basis. So the next demo I want to show is, it's a bit more complex, but nonetheless it's quite a cool little effect. So here we've got some little guys, they're running around, running into Muncie's towers. And you'll see they walk behind things. We want to make sure we can still see our guys when they walk behind. So we might want to do like, if anyone's played Mario on the Nintendo Switch, he has like a little cool little dither effect when he walks behind something. So let's try recreate that. So here we've got on our render pipeline asset, we've already got the unit occlusion renderer that we've made before. So this is already rendering, it's all ready to go. So let's start adding our render features. So first one we want to do is render a dither effect. So we want to render the characters again with this material. So it's very similar to the last setup. Make a new render objects. We can call this dither. We want to override the material here. So we've actually got one here. And because this monitor is extremely high resolution, you can't see the dither effect at all. But if we have a look at the shader, this is actually using Shader Graph. So it's quite a simple node setup here. It's practically just using the dither node, it's built in. And we can use this as an unlit master node plugged into our character. So let's assign this material. Now, he's still behind the tower, so this isn't helping. And if we have a look, it's not actually rendering. So this is because we forgot to set what layer we want to render. Here, I want to render the character again. So here we can see he's now getting rendered with this dither effect, but when he goes behind something, we lose him still. So this is where we want to actually start to override some more stuff. In this case, we want to override the depth. So the character's behind the building, so his depth is greater. So by default, when we do a depth test, anything that's less than the current pixels that are already there will get rendered. If it's greater, it won't get rendered. So we want to flip this around. We want to say if it's behind something, we do want to render it, but if it's in front, we don't. So let's change the depth test. So let's change it from less equal to greater. So here we can see the characters come on top of the tower, but the individual characters that are still running around getting some weird artifacts. Now this is because the characters themselves have quite a lot of overlapping geometry. You'll see the side of the character, his arm is actually behind him. So this is going, well, we'll render the dither effect there because it's behind. This isn't ideal. So this is where we want to actually render the character after the fact. We want to do the dither first, then we want to render the character again. So let's just get to a point where we can see him. And this is where we can use the default layer mask. So this is essentially a layer mask for everything that's, every kind of built-in pass in Lightweight. What we want to do is tell it not to render the character because we will do a dedicated render feature pass for this. So we'll turn off the character. Now, you can see the dither effect's gone away, which is great. It only appears when he goes behind the towers. But now we've lost him. So we need to add another pass. We render objects again. Let's call this one character. And set the layer mask to the character. And now our characters come back. Now, there's something else we'll see here. And this might be, you might look at this and go, wow, this is great, this is perfect, but at the same time, I've also lost my blue color that I had. I had a nice solid blue, which I kind of want back. Right now, the characters, when he goes behind, he gets a dither effect, but he's still rendering with his original colors and textures and materials. In this case, I don't want this. So why is this happening? So what's going on? We'll have a quick look at the frame debugger. Here we'll see our opaques, we'll see our dither effect gets rendered, our character's rendering. Well, why is our character rendering here like this? Now, in this situation, it's actually because the dither effect itself is writing to depth. So the dither's coming in, it's saying, I'm behind something, I'm going to render myself. It renders itself, and then it's actually rendering depth as well. So the pixels here are becoming behind the tower, which means when the character comes to get rendered, the character goes, well, I'm behind the tower, but I'm in front of the dither effect, so I can render, I'm fine. And we don't want this. And an easy way to fix this is actually to make the dither effect not write to depth. So here, under the depth override, we've also got a write depth option. If we disable that, now the dither effect doesn't write to depth. When the character goes to render, the tower's still in the way, and we have this kind of blue highlighting kind of dither effect where the object walks behind something. Now again, this works perfectly fine in the scene view, and is quite handy. Now all of this was done without writing a single bit of code. The shader itself was made in ShaderGraph. The parsers were set up just on here. They already provided the render objects one, and then it's just attached to the lightweight render pipeline asset. So this gives us a nice little way of being able to make these kind of rendering changes that would otherwise take quite a bit of code and make it so it's nice and simple. Now, there is one last demo, and this will be more of just showing you through it rather than the setup. It's a much more complex, but it still doesn't require any code, which is nice. And this is the classic case of a first-person weapon. Now, normally, obviously, you have a first-person weapon, and you render it with a wide field of view that you would normally want in a game like this. You'd have upwards of even over 100 degrees of field of view, and this makes the items that you've got in the first-person view look very elongated and weird. So with this setup, we've actually managed to make it so you can render the weapon with a separate field of view. Now, in built-in Unity, this used to be done you could do it easily with another camera, because you could just make another camera, change the field of view, tell it to render over top, and you're all done, right? But there's some massive downsides to that. Now, you're rendering an entire another camera just to render some objects again. Now, this includes culling, this includes setting up all the textures, this includes a lot of setup and extra costs of switching between them. So, rather than doing it with another camera, we wanted the ability to be able to just render a few objects and render it with a different field of view. So if we have a look at this field, FPS setup one we've got here, we've got quite a few overrides, we've got a few parsers, and these are all set up with very specific settings. But the idea is that we can now override individually on each a camera, and this gives us some basic settings that we could override. Because we're not doing culling again, we don't want to render too far off of what we're originally rendering, because we might miss some stuff. But we're obviously not paying the cost of doing culling again, which is great, because culling is very expensive. So here we can just override some things, here specifically the field of view. Now, there's some other things here like stencil, we're doing some depth overrides. Essentially, all this comes down to is we've got a system that you can go up, right up next to a wall, your gun's not going through it. Now, you might go, well, it's not going through it. But if we go to the scene view here, we can clearly see the gun's actually going straight through the wall. Now, this is because we're doing some things such as stencils to chop out that part of the weapon and tell it to always render, and the other parts of the scene to render around it. And we're also overriding some things such as depth for allowing the transparency to work correctly as well. We will actually show this in much more detail set up on the theatre talk in our booth at Unity on the Friday. So Friday, I think it's 2:30. We will go through the entire setup of this example. But yeah, I mean, I guess I should probably actually show that it's working with the field of view.
And the gun rendering first.
Yes. So, yeah, here we can go to ridiculous levels if you want to see everything around you. But if we have a look at the frame debugger, we'll get an idea of exactly kind of more of what's going on here. So the gun's actually rendering first. So we do this for a few reasons. We want to render it first because we don't want to render everything else already behind the gun. Otherwise, you know, I've been playing a bit of Destiny 2 lately, and some of the guns get pretty big. You know, they take up a good quarter of the screen or even half of the screen sometimes. And you don't want to pay for rendering like 5 characters behind that weapon if they're not even visible. So we render the gun first, then we render the scene. Then we do our skybox, copy color, render our transparencies, and then we want to start rendering the transparent parts. So you might go, well, that's not all the transparent parts. And this is because here we're doing some stencil checks to render just the transparent parts over top of where the gun is. This means we don't have to worry about them intersecting with the wall. They'll always render. They'll render exactly where the gun is. And then when we go to render the rest of the transparent objects in the gun, we don't do the depth test at all. So we're not checking if there's any, we're just saying render it no matter what. And so this avoids the transparent parts of the gun from going behind the wall.
Receive shadows.
Yep, so we can see we're still getting proper shadows cast onto our weapon and casting from our weapon. Obviously we haven't got a third person character loaded in here, so we just got floating arms. So, I think we've got some time for questions.
Yeah.
Hi, what's the status of the post-processing stack with the lightweight pipeline?
Do you want to? Okay. So we're reworking the post-processing to be mobile friendly, where we also stay on tile memory, and this is coming in 19.3.
Yeah, current post-processing stack v2 works. We can't use any effects that rely on motion vectors because motion vectors aren't supported. So motion blur, TAA don't work, and we also don't use AO because it relies on compute. So.
Yeah, so we're working on a optimized AO solution in 19.3 as well. And I'm not exactly sure about the motion vectors, but I think it's coming as well, right?
Yep.
Yep.
Okay, thanks.
Are these pipelines something that would be switched out at runtime? So say I'm like rendering one way and then some effect happens to completely change my render pipeline. Is that something that can be done on the fly?
Are you asking if you can change the render pipeline at runtime?
Yeah.
Yes, you can. It is just, so the asset contains the renderer, and the asset contains some quality settings. So currently, the asset that it is assigned in game view controls stripping. So we're planning to remove this restriction, so the stripping can be configured separate from the asset, or maybe all assets. We check all assets, but you should be fine. You should be okay to change that at runtime. It is. We just don't recommend changing from built-in to lightweight or from HDRP to lightweight because there will be we have to include a lot of shader variants in your build if you do that, so it's not optimal, but technically you can do it.
Follow up, can they be in asset bundles so we can like deliver some new look that'll be for a short period of time?
For the custom renderers, yes. Yep.
Thanks for the great work. Currently, we're using material property blocks to do per object shader property manipulation. Is there a new way? You mentioned that the new batching is alternate to material property blocks. Is there a new way to do that per object that will still use the batching?
So the great thing about it is that you don't have to do it anymore. So you just can make, 100 materials. And if they share the same shader and you're just changing some colors, they all get batched together.
Yeah, so essentially the reason you had to do material property blocks was to remove the CPU cost of rendering some objects with slightly different materials. But now with the new batcher, because we batch per shader and not material, then you don't really have to do that. It should just work by default, like for you.
Thanks.
All right.
Cool. All right.
All right. Thank you, everyone. I just